Okay, I just wanted to do a quick plug for Capture the Flag. It's going on right now. We set up the local network here, the local wireless network. So right now there's 4 online challenges and 8 challenges that you can do by attacking our wireless network. It's HC3 CTF, and if you follow us at _Zerg XRG, we're going to put updates and things in that Twitter. All right, my name is JohnDegruyter. This is my second time at HackerCon. My talk's going to be on Introduction to Linux Exploit Development. And this talk is a training session. You know, I don't have a new 0-day, or it's not going to be anything groundbreaking, but it's basic technical talk. Labs are available. There's a USB stick right here if you want the labs. Also at the Zerg, just tweeted download links for the labs as well, so you can download them. Basically, they're vulnerable Linux C programs and also walkthroughs to exploit each of those C programs. This talk is designed to introduce concepts needed to get started in exploit development. These are old school attack techniques. We're not going to talk about bypassing DEP, stack cookies, ASLR, packs for Linux. We're not going to talk about that. We're just going to forget all that today and go back in time and just kind of see how these things actually work. And why do we want to do this class? Because we want to learn how things work, right? But the real reason is because we want to be like this guy. Hack all the things. Some other reasons, we learn the fundamentals in order to move on to more complex techniques. There's a lot of legacy systems out there with embedded Linux that aren't using the most modern protection. And some of the new systems that do have kind of the modern controls don't implement them correctly. Another thing that's fun to do is there's some challenges out there. Exploitexercises.com. There's 3 VMs you can download for different skill sets. So you just download the VM, fire it up, and you're ready to go. Also, someone just told me about this one. If you just Google for Gera ERA exploits, there's some exploit challenges as well. And the links are in this presentation as well. Lab information. Let's see. Skip this because it's just going to be the download of the tarballs. Basically, it's about 25K instead of having to download a VM. And you can run it on backtrack with just disabling a couple features just for testing. So where do we start? We're going to start with Hello World. Why not? The source code's right there. It's a very simple C program for x86, and we're just going to kind of break it apart and look at it and see what it does like under the hood. To compile the binary, very simple. If you haven't done it before, in Linux from the command prompt, GCC, and some of the options we're going to do is -ggdb. And -o tells it the output file is just going to be hello. ggdb allows you to look at the source code while you're debugging it instead of just the assembly language. So what just happens when we run that compiler? Basically, the compiler takes the source code file or files and creates object code and object files. And then the linker takes those object files, tells them how to communicate with shared libraries, shared objects, and then it creates a binary file, which is executable. And that's our executable. ELF contents, I'm going to go over this pretty quickly. Basically, there's a ELF header file, a program header table right below that, and there's a section header table further on that kind of links all of this stuff together. There's more sections in there, but it kind of looks like this in general. You have the ELF header, the very first part of the file, program header, and then you have different sections. Some of the sections are things like BSS, which is uninitialized data, but it needs to create space for those variables that will be initialized later on in the program. Data, that's where variables are stored. RO data, read-only data. Text. .text is where all the source code is. Things we can see by just examining the ELF without putting it in a debugger. Things like assembly instructions, we can disassemble it. We can see which files are linked to it that it needs to run. And of course, we can break it apart and look at all the header information. And to do that, we use tools like object dump, readelf, LDD, and strings. And there's a walkthrough for ELF, a lab in there that allows you to read all those things and kind of see what's going on with the file. Object dump, you can get header information, pull out different sections, disassemble them, look at the hex, look at the different functions and how they map if they are initialized. Readelf, it allows you to look at, -H allows you to look at header files, some cool information in there, so you get the magic number, entry point address, so where the code starts, you get the program section offset, so how far down into the file they are. LDD prints the shared libraries required by each program, so what it's linked to. You can see what, so you can see that with LDD. Hex dump, you can see data like magic number. You can look at actual hex code in the file. And strings, you can just look for interesting stuff in the binary. So there's a lab. I'm not going to walk through it, but you can walk through that in the exercises. Does anybody need the USB? Yep. All right, so let's start with the basics. We're going to get into some assembly here. How many of you have used assembly, written assembly, reverse engineered? Anybody? A couple people. All right, cool. So, so the CPU has registers in it, which are small chunks of memory that's in the CPU that it operates on that can access these very quickly. Here's a list right here. Some of the main ones we're going to be looking at are EIP, which is the instruction pointer. That points to the next, points to the current instruction that's being executed by the CPU. ESP is the stack pointer. It points to the top of our stack frame, and I'll show you some illustrations of that here in a minute. EBP points to the bottom of our stack frame. EAX is the accumulator, deals a lot with passing data to functions, passing data, getting data back from functions, getting results. These are general purpose registers, so from EAX on down, they can be used for various things, but in generally, this listing is what they're used for. Okay, so when we compiled hello, it created a binary, and it created an object file. So we can see that by disassembling the code. And we can also see that by just running a debugger. And we're going to get into GDB, which is the debugger we're going to be using in the labs. But I just wanted to run through some assembly real quick just to kind of get you familiar with it, get you used to seeing it. This is the main function in our hello program and what it looks like in assembly language. So what it does, it pushes the EBP register we just talked about onto the stack. And we'll get to the stack in the next slides. It's kind of chicken or the egg, so I chose just to show assembly first. But it's going to push EBP onto a stack. It's going to move ESP into EBP. It's going to AND ESP with FF, FF, FF0, just to kind of mask that. And it's going to subtract a value from ESP. And it's going to move an address into EAX. And then it's going to move EAX into the value of ESP. Then it's going to call the printf function to print the string hello world. And then it's going to return. So what does all that mean? So we talked about the stack. So in the Linux process, the stack is a portion of memory that you can see toward the top there. But it's a data structure. And it's last in, first out. And the way they explained it to us in school was a stack of plates. And you can only take one plate at a time, right? So I can set one down, set one on top of it, set another one down, but I can't get that bottom one without pulling the ones off the top. So it's a last in, first out data structure, and it grows down in memory. So this part's a little confusing, but if you think of like a stalactite in a cave, how it grows down, that's what the stack does. When you add to it, when you push a value on top of it, it's going to grow further and further down in memory address space. It's used for passing parameters to functions and also holding local variables in the functions. It's also used for keeping track of function calls and being able to return back to another stack segment. And like I said, it grows toward low, shrinks down to high. And you can see the registers. EBP is the base pointer, so that points to the base of the stack segment that we're using. ESP points to the top of the stack segment that we're using. And if you have any questions, just feel free to ask me as we go along here. So this is a push instruction. So what happens when we push EBP? We talk about that in the assembly language. So what it does, it takes the value of EBP. Say this is our stack in phase 1. So EBP is at 0x BF FF F0. I'm sorry, BF FF 0018. So that's the value of EBP. And ESP points to the top of the stack, so that's at address BF FF 0008. Points to the top. The value at ESP, we note that by if it's in parentheses, it's talking about the value of the register of what's contained at that address. So the value at this address is all ones. It's 8 ones. And the value of EAX is dead beef. Okay. So what happens when we push EBP onto the stack? Remember, it's a stack of plates, so we push this value onto the top of the stack. Okay. So a copy of EBP doesn't change, but the value gets pushed onto the top of the stack. And when that happens, the stack pointer, which points to the top of the stack, automatically increments up. But it's actually, remember, the stack grows down. So these memory addresses are actually inverted. So it's growing toward lower address space. So our ESP changed and our value at ESP changed, but nothing else changed. Okay, does that make sense? And then the pop instruction. So this is the opposite. So if we start with this, basically it's going to pop a value off the stack. So it's going to pop the value of ESP, which is this data right here. And it's going to pop that value into EAX. So pop EAX means pop off the stack into EAX. So it takes this value, stores it into EAX. EAX changes from this to this, and ESP goes down one value in the stack. So it goes back down to where it was. Okay, so if you have the labs up, I'm just going to go over it real quick. I have a little cheat sheet here. So what we want to do, we have hello and hello.c. We can just compile it real quick, and these instructions are on the lab, but we're going to use gcc-o for hello. We're just going to name the binary hello. We're going to use the ggdb parameter to get the debugging symbols, and we're just going to give it hello.c, which is our source file. And what that does is overwrites the hello that we currently had. So now we have a binary file that we can run, and it's basically hello world. You see that right there. Okay, so what does that look like in a debugger? So we're going to use GDB, which is a debugger. I believe it comes with Linux. But we just do GDB hello, and that opens up that binary. And it doesn't run it. It's ready to run, but it just opens it up for us to look at. Some of the commands we can do are disassemble, or you can just type DISAS for short, disassemble main. And that shows us the assembly code of what we just looked at the source code for. Right, push EBP, we know what that does, pushes EBP to the stack. Another thing, since we use the -ggdb, we can do list, which gives us the source code as well. So if we didn't have debugging symbols, we couldn't see that source code as well. So in GDB, you can work with things, you can work with the source code as well with those symbols. All right. Okay. So if we want to run the program, you can set breakpoints, and breakpoints will stop the program as it's running at different areas. So we can do break main, and we just set a breakpoint at main. So as soon as it gets to that main function, it's going to stop. And we just type run, and it says breakpoint main is hit. So it started running it, and it stopped. So it's ready to print hello world. So if we look at this as main again, it shows us the code, right? And if we want to see what the instruction pointer is, which is EIP, which is the as it executes, EIP is each of these values as it goes down the line and executes each instruction of code. So if we want to see EIP, we can do examine /wx $EIP, and that shows us where we're at in the program. So we had it break, and it broke at 0484A0B8, which is oh, I'm sorry. It's actually 80483CD, which is right here. So we're just about ready to move this address into EAX. So what is that address? So it's a very simple program, and we're just going to print out a string. That string has to reside somewhere. So another command you can do is x-ls in the labs, and the value of that address. And since it's hex, we type 0x 080-484A0, right? And that shows us our string. So what we said was, I want to examine a string at that address. And we say string because it doesn't know how to present it to us, so we tell it it's a string. Mm-hmm.
What is the significance of the value after the +sign?
Okay, that value is, we can look at it a different way. So it's shown it to me in hex. So let's say we want to look at it as an instruction. So we do, right. Let me do this real quick. Examine. Okay. I'm not sure. That might have just run together with a different value. Okay. I'll look at it. I'll look that up later and get back to you. Okay, so there's some different things we can do. So examine, we can look at the next 10 assembly instructions, if we forget where we're at. Let me do that again. So we can look at the next assembly instructions. We can do look at all the registers. If we do, we can type info registers, or for a shortcut, we can type IR, and that gives us the value of all the registers there. So there's more things in the lab, but I'm just gonna move on here. I'm doing it this way so I don't have to switch in and out of full screen with PowerPoint. Okay, function calls. So we saw that the hello world calls printf. So what happens when we call a function like that? Well, each function has its own section of the stack, and that's called the stack frame. So remember, we have our stack, and the section between EBP and ESP is used by the current function, and that's called a stack frame. So for example, we have main. Our main stack frame, that function uses variables and addresses between EBP and ESP. And then when printf is called, it shifts up. So EBP is going to shift up and ESP is going to shift up, and printf references variables between the base pointer and the stack pointer here. So whatever it needs to use to do this printf, it's going to be right there on the stack for it. And then it returns back to main. So it'll go up, and then it'll come back to where it was. So when we call functions like that, we need to remember where those pointers were on main when it calls printf or when it calls another function. And this is done by using a common series of instructions called the prologue and epilogue. And also we need to know where EIP is. So to do that, we take EIP and store the next instruction after call, and we store that on the stack, and you'll see that here. So there's a program on the labs. It's called Verify Pin, and it has the prologue in it. All the functions will, but it's push EBP, move ESP to EBP, and subtract a value. The value it subtracts can be any value. It just depends on the function and how much that function needs to work with. But it subtracts that from ESP. And then the epilogue, which is leave and return. Okay, so the prologue. So these functions, we're going to see what it does, but it saves these values onto the stack so that it can come back to it. So from our main function, we call printf again. What it's going to do with EIP, right after this call, the next instruction, it's going to store that onto the stack, and that's going to be stored EIP. So when it comes back, it's going to grab that value and execute whatever code is there. Okay, so it pushes EIP onto the stack, which is our stored EIP, which is right after the call value, also known as our RET or return address. And then the prologue happens. So it's going to push EBP. So it's going to push the value of EBP onto the stack, right? And then ESP moves up. And then it's going to move ESP, the value of ESP, into EBP, which makes that match. So the value of ESP got moved into EBP, so now it points to the same location. And then it's going to subtract a value from ESP. And remember, subtracting moves up the stack because it's growing down. So whatever value it subtracts, maybe it's the length of the local variable or it's the length of an argument. So that's how much it knows to subtract. So now the printf function from hello world would work within this stack frame. And just keep in mind we have stored EIP and we have stored EBP here as well. So the epilogue. So after that function executes, how do we get back? It's also known as leave, but we want to return to our previous stack frame. So what it does is moves the value of EBP. So this value, it's going to move it to ESP. So ESP is then going to match EBP. So it's going to move that. This is also known as leave, and you'll see it as leave in GDB. So that gets moved down, and then it's going to pop. So it's going to pop off the top of the stack and store an EBP, whatever's at the top of the stack, which is our stored EBP. So that's going to get popped into this value and send it back down here. Now, ESP points to our stored EIP. So what it does after that is pops this value, which is the instruction right after our call command. It pops that value into EIP and executes it. And this is where buffer overflows occur. And this is why it happens. Okay, just went over that. And the leave and the pop in EIP is the ret. Okay, so buffer overflow, how does it work? Basically, it happens when a stack-based buffer overflow happens when a variable cannot contain all the data that you copy into it. So in this example, this is the same stack. I just flipped it horizontal so we can just have a better look at it. So say this variable holds 4 bytes, and then we have the stored EBP and the stored EIP right after that. But the string copy command, or stir copy, it doesn't check the value. What it does is it copies the second argument into the first argument. But the problem with this function is it doesn't verify in any way the value of pin that it can fit into P. So the problem is this P can be any length, but it's going to blindly copy it into a 4-byte character array right here. So what does that mean? What if we had something that was 12 bytes? So each of these are 4 bytes, EBPs 4, EIPs 4. So what if we had something in this example that's 8 bytes, right? When that string copy happens, it just gets copied over. It copies over P4, and it can copy on past that and copy over the stored EBP and the stored EIP. And it just gets overwritten with garbage. And when the function tries to return to the stored EIP, it's going to try to return to AAAA, which isn't a valid address. So it's going to give a segmentation fault and crash. So, I'll just explain. So the trick is we want to control EIP. So we want to overwrite that with an address that points to code that we control. And that's kind of the game behind buffer overflow attacks. So instead of using just A's, we want to put a little thought behind this and overwrite that with an address. So that's what we're doing here. And we have to align it perfectly so that only 4 bytes are overwritten, only the 4 bytes of EIP. Now, ADDR in this example was going to be an address that we control. And it's going to be where our shellcode or our NOP sled to our shellcode will be. So a little bit about ADDR. It's going to be a 4-byte memory address. When you write it, we're going to use Python, but when you write it in hex, it's going to be a -x. And the address is little endian, so the bytes are in reverse order. But this is going to be what points to our shellcode. Now, we haven't figured that out, but we're just looking right now about how we overwrite EIP with memory addresses. So if we want to jump to the address BF, FF, FA32, we have to write it -x, which means it's hex. If not, it's going to try to translate it as ASCII lowercase b as a single byte. So, and we write it in reverse order, so /x BF, FF, FA32. And that's how we write our addresses when we overwrite EIP. Okay, so we craft our buffer to look something like this for right now. All right, so it's going to try to jump to that address. Right now, we don't know where that is or if it's even valid, so it's probably just going to crash again. But the idea is to get it to our shellcode. And shellcode is just a small piece of code that we want to execute on the system to gain more access. And it can be to start a shell, it can be to open a port, add a user, whatever you want to do, but you got to fit it in a small enough size to fit into the buffer. They're typically written in assembly, and when you which is when you write the shellcode, you want to be careful of bad characters. So in C, definitely 00 terminates the string. So if you have shellcode and it's 30 characters long, and there's a 00 in your shellcode 5 characters in, when it copies that over, it's going to break at that 00 because it thinks it's the end of the string. So it's important to be wary of what characters you have in your shellcode. The shellcode that we're going to use in the examples are just simply execute bin/sh, which will give us a shell. And below that, there's some shellcode for the same thing, but I had to do this to get it to work in one of the challenges because when you try to execute just the bin/sh against gets, it didn't work. It just kind of killed the input. Okay, and shellcode example, I mean, this is just something you can download from exploitdb.com. But basically, you see the hex, that's the string that we just saw. And beside it, sometimes they'll put the assembly instruction. So this is what it's doing in assembly, and this is the string we want to use. So this isn't that important to us right now. Okay. So getting shellcode, where can you get it? Metasploit framework, MSF payload. You can use that to generate your own shellcode, and MSF encoder will encode that for you. Another nice tool is Metasm for creating assembly instructions. So if you want to jump 4 bytes, you can use Metasm to get those hex characters that you need to jump 4 bytes, or vice versa. And Metasploit has Metasm shell.rb included as one of the options, or one of the tools within Metasploit, which is pretty nice. NOP is another important instruction. So basically, it's an assembly instruction that does nothing. It's hex 90. EIP, if it sees NOP, it's just going to continue to the next instruction. So you can use it for padding like we do in buffer overflow. So we can have, in this example, like 1,000 NOPs and then our shellcode. So when you jump, you don't have to jump directly to the address. You can jump somewhere in the middle of the NOP sled, and it'll slide all the way to our shellcode and execute. Another important instruction that's good for learning is int.cc. Hex cc, it's an interrupt instruction, but that just tells the debugger to break and halts the program. So if you're executing this in GDB, as soon as you hit XCC, as soon as EIP sees that code, it's going to stop and give you a signal. So if you don't want to set up your buffer and copy and paste your shellcode around and play with it, the first thing you can do is just use a bunch of CCs. And if you can get EIP to, if you control EIP and can jump into your hex CC and it stops, then you know you can control EIP and you can point it to an area of memory that you control, which you would replace with your shellcode or NOP sleds. So Stack Overflow, we talked about this a little bit when we saw it horizontally, but basically it's writing past, this example is writing past our stored EIP. We want to overwrite EIP with an address, but sometimes we don't just have the buffer, we can go past the buffer and past EIP. So say it's getting ready to call a function. It has our stored EIP, stored EBP. Of course, this is how it knows to get back to the previous main stack frame, which we talked about. And we have the do stuff function, which is just a random name for a function. But the do stuff function has local variables in it. So remember, we talked about the stack frame is going to hold the variables that we need to execute do stuff within that area of the stack. But if there's a vulnerability and we can overwrite that, like the buffer overflow we just looked at, potentially we can overwrite EBP and EIP again. But also another thing is that we want to have the address exactly right so that we can jump to our shellcode. And if we can write past EIP, we could put our shellcode there, past the instruction pointer. So this is used a lot because sometimes if addresses are hard-coded in, you can find somewhere in the process space where you can find a jump ESP. And if you can find a jump ESP and you control the shellcode after EIP, that works out really nice for you, because when the stack frame goes back in the epilogue, it's going to move ESP just past the EIP we overwrote right here. So we know that our shellcode will be at ESP because that's the value right after EIP. So we can put a NOP sled here to our shellcode, or we can just put our shellcode there if we can get the address exactly. So basically this address, you overwrite it, it does the epilogue, moves the stack frame down, and then it pops the stored EIP to execute. So this address points to jump ESP, and jump ESP is going to jump the instruction to ESP, which is right here, which holds our shellcode, and we get code execution. So what we want to do when we write these buffer overflows for these labs is we want to cause it to crash, and then we want to see if we can overwrite EIP. Then we want to find the distance to EIP, and then that tells us how big we need to make our buffer. And then we got to figure out where we can store our shellcode. Is it inside the buffer? Is it past EIP? Or is it somewhere else completely? So when we find that out, we put our shellcode there, and we point EIP to our shellcode or our NOP sled. Okay, to do this, we're going to be using Python. Just some basic Python that helps out with this stuff is pretty much all you need. But we run it from the command line, Python-C. You hit your parentheses, single quotes, A times 1,000. Prints A 1,000 times through the screen, pretty easy. And then we can pipe that to a program and try to crash it, or we can pipe that to a file and then cat that file to the program, or run it as input to the file in other ways. Okay. So for these labs, to get them to work, we need to turn off ASLR. And to do that, there's instructions in the README file. Warning, don't do this on a production system. This will make your system more vulnerable to attack. You just at your own risk. So just in your test VMs, and when you're done with this lab, turn it back on. So what are some mitigation techniques that we're disabling right now? So ASLR is address space layout randomization. So remember how we want to jump to ESP, or we want to jump to an address that has our shellcode? If we have a hard-coded address that works, and we have an exploit that works, and we're using those addresses, it's going to be a problem with ASLR, because ASLR is going to randomize the segments of memory at runtime. So we might have jumped to that the last time the program ran and it worked, but this time when the program runs, it's going to be different addressing. So it's not going to work for us. Another thing is stack cookies. So remember how we have EBP and EIP? Stack cookies are used by the compiler, or the operating system when it runs the program, but they're put on there by the compiler options that puts a cookie right before EBP. And if you overwrite that cookie and overwrite EBP and EIP before it returns to EIP, it's going to check that value. And if it's overwritten, it's not going to work. It's going to cause the program to halt. Another thing, another protection we're going to disable is a non-executable stack. So with a non-executable stack, that section of memory that we're jumping to where our shellcode is going to be isn't even executable. So we're going to turn that off as well. Disabling ASLR, to check if it's on, as root, you cat /proc/sys kernel randomized VA space. Now if that's a 2, which it likely is, ASL is turned on. So you can set that to 0 for these labs just by echoing 0 greater than sign into that file. And it should come back on after a reboot, or you can just echo 2 back into that. Now, disabling stack protection is different. It's not a setting. It has to do with the program when it's compiled. So when we compile it, like when we did the -o option in -ggdb, we're going to use -fno-stack-protector. So that'll disable the stack cookie. And the executable stack, to disable that, we do -z exec stack. So it's going to look like this. GCC-o verify_pin, which is one of the samples, -z exec stack -ggdb -fno-stack-protector verify pin.c. And that's going to compile it so that it's vulnerable, so that we can play with these old school exploits and kind of learn from them. Okay. Any questions? Okay. So if you want to follow along in the crash lab, so the challenge here is to get the program to crash with 42424242. And to do that, we just want to set up a file with a buffer in it. So we can do Python So that's just going to print A to the screen 100 times. So we pipe that. We can pipe that to a file, a.text, and we can do it in GDB. So if we go to GDB, we can do run > a.text, and that's going to take that file as input into that program. Sorry, I'm going to do GDB welcome, which is the first challenge. So we crashed it, and it says it can't execute 41414141. So what that means is that EIP was overwritten, and so we want to know how big of a buffer we need to overwrite that. All right, and we can do this by doing different values. Instead of doing 100, we can chop it down to 50 and then 75, and just kind of do it by process of elimination. But I see it's 12:30 right now. You guys want to break for lunch? Anybody, or you want to keep going? Okay. All right. I'm just going to keep going then. All right, so that's an exercise. That's an exercise for you to do to try to get that to come up correctly. Okay. All right, let's do another lab. Let's do int lab. So what we want to do is get this to jump to an interrupt, or -c, or sorry, hex cc. Okay, So to do that, the answer for the last lab is actually in this one. But what we're going to do is create a Python file. Yeah.
When you all finish with this particular talk, do you have any more minute? How long is this one going on for?
It goes till it's another hour on top, but I'm just going to keep rolling. So it's supposed to go from 1 to 2. So I'm just going to keep going through and.
All right. If it doesn't, if you stop before I get back, just have someone push the green button. The orange button there.
Okay.
And hit the red button there.
Okay. Cool.
Thank you very much.
Okay. Cool. Thanks. Okay. So what we want to do is create a buffer that is going to overwrite EIP and that's going to write a bunch of interrupt commands. So we do that. So that's going to look like that. So that's what our buffer is going to look like that we're going to send to it. So we're just going to pipe this into a file. We're going to call it b.text. We're going to run GDB again with welcome. Right. Those are our hex Cs. So hex CC, which is an interrupt. So what we're going to try to do is overwrite EIP here. We got to figure out where it needs to overwrite, where it needs to jump to. And we're going to try to jump that into our buffer, which is somewhere in here. So we should have a pretty good shot at it. And since there's no restrictions on writing past EIP, we can do that here. So before the buffer it was 78 A's. So we have 78 bytes to do our shellcode. Now, real small shellcode we could put in there, but since we have all this space, we're just going to do it this way. So we're going to run GDB welcome again, and then we're going to run it with b.text as input. And it says program received segmentation fault. So we crashed it at 424242. So we're overwriting EIP exactly with our B's. So let's do this again. So I want to look at main, and I want to break right after the vulnerable function. And we know it's string copy. I'm sorry, it's gets. So we have our gets instruction here. So I want to break right after this call because this has just, this vulnerable function has just messed up our buffer. So right after this, I want to look at it and see how it overrode it and where I can put my shellcode. Yeah.
Normally when you're using GDB, it wouldn't include that level of detail, right? Except that you did dash GDB.
No, it will include this. It will include the assembly. If I do lists, that's the detail that you get with GGDB. That gives you debugging symbols. So instead of breaking on the address after main, I could break on a line number. So that's what's nice about it. But okay, let's go back to take a look at it. So okay, so there's our gets function. We want to break right after that. So break, and when you break on an actual address, you use a star. If not, it's going to think it's some sort of variable name. So break 0x080.484.B8. So we have a breakpoint there. Okay. So when our code, when EIP gets here, it's going to stop. So we can type run. We don't have to put in the parameter for B again. It'll do it automatically. Start from the beginning. Okay, so it's stopped. And you can see some of our variables have been overwritten, so something messed up's happening to it. So what we want to do is look at the stack pointer. Remember, that's at the top of the stack. So we use the command X, which is examine, and let's say like 30 words, which is 4 bytes, and we want to see it in hex. And we want to start at ESP. Oh, wow. Okay, I'm just going to make this screen a little bigger. Okay, that's kind of hard to see. Yeah, I apologize, it's a little hard to make out, but we see that these addresses correspond with 4.1, which is the ASCII characters for our A's. And then as we go down, we see 4.2. So these are our B's right here. And then after that, we start to see our C's, which is our buffer, right? Which is that long section of C's we added right after that. So really, we can pick any address. So let's say BF, FF, F4, F0. If we jump to this address, override our B's, so when EIP returns, it's going to jump right here to this address. And it's going to hit XCC, which is an interrupt instruction, so it's going to break. F4, F0, right? So BF, FF, was it F4? Just do F0. And we'll write that to C.text. Okay, so now we have another buffer. And this one, instead of B's, it's not going to crash on 42424242. It's going to jump to that address, which hopefully will land in our C's. So we can just run that. We didn't do any breaks or anything, but we see we received sig trap, which is the debugger trapped it or stopped the process. So now where are we? We're at that memory address we jumped to. We're right there in our code execution. And we can do examine the next 10 instructions starting at EIP. And you see there that these are interrupts. We examined it as an instruction. We can also examine that as hex, right? So that's where we're at. That's where we're executing. So we successfully overwrote EIP and jumped into code that we control. So what do we want to do next? Right, exactly. Okay. So on the labs, there's a tools folder with shellcode in it, so you don't have to type it. Yeah, you do. And the next example was a very small buffer, but on this one there's no restriction and we're writing past EIP, so we can write all the way to the end of the stack if we want to. So we have a lot of space right here, but absolutely when we putting it before EIP, we want to make sure that's measured out to be exactly the same, so that we don't shift it past EIP or anything like that. Okay. So we're going to get rid of these C's. We're going to put some NOPs there, 300 of them. And then we're going to paste our shellcode. Okay, that looks somewhat right. So we're going to put that into a buffer, and we're going to call it d.text. So again, we're going to run gdb, welcome, run, right, so c.text, right now, sorry, d.text. So this should execute that shellcode, which is bin.sh. So it executes, we see it executes a new program, bin.sh. So basically we broke out of code execution and jumped and redirected it to do what we want, which is execute shell. Now, what does this look like outside of GDB? So we can do things like cat d.text, pipe it into welcome. I think that's not going to work, but something else might. Hold on. So that was the shellcode for gets and GDB. So we're going to try it with just exec CVE and see if that works. It doesn't. So I'm not going to mess with it anymore. I'm just going to move on. But all right. So back into Python, some of the things we did was, we use CC or the interrupt instruction. We can jump back into the buffer into it, or what we did in the example, we put it after our overwrite. So we put it right here and jumped into it that way. And we can jump, same with NOP-SLED to shellcode, we can jump back into our NOP-SLED to shellcode if we have enough buffer space for our shellcode, or we can jump forward. Okay. Right, and like you said, Lee, when we do it before EIP, we want to make sure that our length still matches so that we overwrite EIP precisely. And a quick way to do that is to just copy it, just run Python x equals, you can put the variable for your shellcode, and this len, whatever you set it to, and it'll tell you the length of your shellcode. Okay, we just did that. Another way to do this, Metasploit has a tool in there called pattern create, which is very nice for creating these buffers. So before, when I was trying to figure out what the length of the buffer was, instead of doing 100, 50, 75, and just kind of doing it manually, you can do a cyclic pattern, which is basically if you pick like 3 or more of these characters, they're going to be unique within this substring. So we create a pattern of 100 bytes, and it will create this for us. And we crash it, and when EIP, when it gives us an error, we're going to see what overwrote EIP. And so if it's AC0 AC, we can take that value and put it in a program that they provide called pattern offset, and it'll tell us how far into it was. So it'll tell us it was 80 characters in, or it was 30 characters in. So that's a good way to get your EIP, find it, and get that set up before playing around with doing the buffers manually. And another way to do that, if you don't have Ruby, is just have that. What I did on here is just exported that 500 character cyclic string to PC500.txt and created a script that basically does this and finds the pattern for you. So it does it in Python, and you have a 500 character script. So you don't need Ruby, you don't need Metasploit to do this. Okay, so what if you have a small buffer? So you have a small buffer and you can't write beyond EIP. So in this example, it's a 20 character buffer. So we can't really fit shellcode in there. So we have to find another place to put our shellcode. And one of the things we can do is use an environment variable. So they're addressable within the process for that user. To create one, you just do export, whatever you want to name it, equals, and then the value. And then you have that environment variable that you can reference with $. So what we can do if we have a small buffer is to put our shellcode in an environment variable like that. So this example shows it here, but we're going to do it in the lab as well. So once we have that variable in the environment, so we want to know the address of where that's at so we can jump to it. So what I do usually is go into GDB, break at the function, and do x slash like 5,000, and look for and start at ESP. That S at the end is a typo. It should be X, and then look. Basically, we're just looking at the stack 5,000 characters at a time, and just scroll down through it until you see your NOPs. And that's, if you jump somewhere in those NOPs, it's going to just do no execute all the way till it gets to your shellcode. Another thing, there's a tool on the in the tarball, but it just basically gets an environment variable with the C program. And it's a pretty common tool, and it'll show you. So if you do get an environment, so in this example it's shell, so address of shell, it'll show you the address where that resides at, and it'll show you the string that's there. Okay, small buffers. So what this program is just basically, it takes a pin number. This is just something I wrote pretty quick, but if the argument is greater than 20 bytes, it's going to say it's too long, and it's going to tell you you need to input something that's less than 20 bytes. Okay. Actually, I'm sorry, it chops it off. It'll concatenate that and send 20 bytes at a maximum to the function of verify pin. And what verify pin is, it's a character array of 4 bytes, but it has string copy. So if you can get up to 20 bytes, it's going to overwrite that, and you're going to have enough to overwrite EBP and EIP, but you're not going to have enough to put any valuable, any shellcode in there to really do anything with it. And the rest is just basically just to make it look like a real program, but just does a string compare at the end there. So basically we want to create an environment variable. My shell equals, and the $ parentheses is just saying to execute what I'm putting in parentheses here. So we're going to print 1,000 NOPs plus shellcode. Okay, so it's going to create this myshell variable, and if you do echo shell, it's going to see this is our huge NOP sled, and it goes down to our shellcode here, which is going to execute bin sh. So now what we got to do is find an address somewhere in here that we can jump to. And we do that in GDB. Okay. So main, have our verify pin function. So I'm just going to break in our verify pin function and run with it's 24 bytes. I'm just going to continue it for the first time, but 454545, we know we're overriding EIP, and 45 is E. So that's where we want to put our address. But we also want to see our shellcode, so let's run it again. So we ran it and broke. What I usually do is examine 5,000 words of hex starting at ESP. And it usually gets you to it pretty quickly. Some A's. Okay, so here we are in our NOP sled. So we can just basically pick one of these addresses, and since it's ASLR, it's not changing when it starts up. Any of these will work. So run, instead of what we had last time, we can just do Python. So this is going to run it and jump us to that address, which is our NOP sled into our shellcode. And looks like I'm missing something here. Because when we crashed it the first time, it was, I believe it was at, the first four, A, B, C, D, right? And we crashed at E, so 4 bytes for each of those, so 16. That's how big the buffer is before we overwrite EIP. And I could have found that by trial and error or doing the cyclic patterns and finding out where it overwrites. So if we run this, and we have the breakpoint, so we just continue, and it executes a shell for us. Okay. So, I mean, that's okay. We're at root, but the issue is like when you find programs that have a set UID, so they run as the user ID, which might be higher privilege than you are. So if we look at these are all ran by root, right? ran as root. So what really makes these kind of attacks work, and where the problem comes, is when these are run as root, but lesser privileged users can operate them. So let's see. Yeah, exactly. So if we do cmod e plus x, right? Right, so this verify pin is going to run as root, no matter which user runs it. So this is student. So if we go to, let's see, actually, this is in the root folder. So that process now is running as root. So if I can exploit that as a user and basically hijack control of that program and get it to do what I want, then I get root. So the same exploit works. Let's see. 1 second here. So student shell. So same thing as a student, I can do the same thing. GDB verify pin. Break. Break verify pin. Run. Examine 5,000 words X. ESP. Sorry, got to run it. Basically, I'm just doing the same thing as a lesser privileged user, but I have an address. Run it again. So run it again. I get shell. It doesn't give me root access here. Let's try it. Let's try it from the command line. That might be because it's in a debugger. So same command. Python. forgot something there. All right, there's probably something I'm missing there, probably something minor, but the instructions and the challenges, and the walkthroughs, they work fine. So if you have any problems or any questions with any of those, let me know. That's pretty much it. That's all I got. You guys have any questions for me now? Okay, thanks.